All right, everybody, welcome back to the relativity videos. In the last couple of videos, we've been talking a little bit about time dilation and length contraction. So talking a little bit about how clocks slow down, or if you're moving relativistically fast, less time passes in your frame, and how lengths actually also contract. So how if you're an observer looking at somebody moving relativistically fast, you see that object or that somebody shrink in length. And so essentially what we're doing today now is we're talking about how to put all of that together. Um, all of that kind of goes together in something called the Lorentz transformations, which is really helpful if you're trying to describe an event from two separate points of view, one who is moving and one who is not. It's also something that you could use to describe one person moving relative to the other, though I tend to just kind of stick to time dilation and length contraction separately if I need those. So I tend to use Lorentz transformations more for, you have some event happening and something's moving relative to both me and to somebody else, and I want to kind of see how that event transforms between both of our different points of view. So yeah, without any doubt, wait, that doesn't make any sense. I'm sorry. Without further ado, there we go. That's what I meant to say. Without further ado, let's go ahead and get into our notes. And I think I'm probably going to leave that part in because it's kind of funny. I had no idea what I was saying there. Anyway, um, all right. So, like I kind of mentioned, the Lorentz transformations are kind of just a more general version of the Galilean transformations, right? They account for both time dilation and length contraction. And so I want to draw a picture to kind of illustrate all of this. So you want to imagine that you have essentially two frames of reference, and that could be two observers. Again, we're going to stick in one-dimensional motion, so I'm not going to bother drawing like X, Y, and Z axes. I'm just going to draw essentially like two axes, one to represent frame S and one to represent frame of S prime. And this is going to be kind of like our x-axis, right? The vertical lines are just me kind of saying, okay, you have two separate frames of reference, and I just want to kind of distinguish between them a little bit nicer. So what we do is we assume that both of the frames were coinciding at the origin and both of their clocks started at the same time. So we're assuming that the very beginning of whatever motion we're tracking or whatever event we're tracking, x was equal to x prime was equal to 0 meters, or whatever unit you end up using. And then likewise for their timing, they should both start their time at the same time, that being at 0 seconds. And essentially what we have is two different frames of reference again. You've got S, who's the stationary frame of reference, and you've got frame S prime, we're going to say is moving with a constant velocity of u in the x direction relative to S. So S is the stationary, S prime is the moving. And as you can see in the actual bullet point, all of the unprimed or unapostrophed letters correspond with frame S, and all of the ones with apostrophes correlate to the frame of S prime. And so kind of the biggest question that we have to get to the Lorentz transformations is if you imagine that there is something happening, and that something maybe happens at this point right here, at a point XYZ in frame S, and it happens at time t. So that means that we could kind of put four different sort of letters to go along with this event right here, which I'll call point P. It happened at point P, at which is located at X, Y, and Z in space at time t. And typically it's common for us to denote the time coordinate as c times t just to give it units that are corresponding with distance like x, y, and z have. So our question that we have is, okay, well, if we know t, x, y, and z, what are t prime, x prime, y prime, and z prime? And again, x is relative to the origin, or relative rather to frame S, who is stationary, so still at the origin, if they're the ones observing the event, so that distance right there is x. Well, what length contraction tells us is that the distance between S prime and point P, x prime, should follow the length contraction rule. And so what that allows us to do then is that allows us to express either x prime in terms of x, or we can express x in terms of x prime. I'm going to do the latter. So I can say that by length contraction, x equals x prime over gamma, which again is our Lorentz factor, the 1 over square root of 1 minus u squared over c squared. But then on top of that, I also have to add the fact that frame S prime is moving. So I would have plus ut. So that actually allows me to relate the distance from frame of reference S to the event at point P, as well as the distance from S prime to point P as well. Well, if I rearrange that for x prime, because remember, we're trying to solve for x prime in terms of x and t, we end up getting that x prime equals gamma x minus ut. And gamma again, just so I want to write it out at least once so you can see it, is equal to 1 over square root of 1 minus u squared over c squared. And so that is actually how we can solve then for x prime. So if we know x and t and u for that matter, we do actually have to know how fast frame s prime is moving relative to s, then we can find x prime. And if we go on to the next slide, you will, or the next sort of thing, you'll actually see that right here. You can actually do a similar derivation to solve for t prime in terms of t, u, and x as well. You can see the results on your screen as well. So now we actually have relations between x, u, t, and x prime and t prime. Now you might be wondering, okay, well, what about y and y prime and z prime? Remember, we're in one dimension, so y and y prime are the same, z and z prime should also be the same as well. We only actually really care about x prime and t prime right now. We care about how things are moving in one dimension. So that's actually quite nice then. It gives us a nice, lovely little relation. Well, if the event that we had, I probably honestly shouldn't have deleted that annotation, but if you have like some event happening and that event is also moving with some velocity relative to both s and s prime, then you can actually figure out that event's velocity or that thing's velocity relative to both frames, relative to one frame of reference if you know it in the other as well. So I'm going to actually just go give us a quick rough sketch of frame S and S prime again. So there's S prime. Imagine that you have something right here that's moving with some velocity v relative to S. Well, we could actually then figure out the velocity of that same event relative to S prime then. Remember, S prime is moving at a velocity of u relative to S. How you can do that is you would be looking for the velocity of v prime. So what is the velocity of this thing relative to S prime? Well, you could probably figure it out quite nicely. It's actually just going to be equal to delta x prime over delta t prime. And if you solve for that, you actually end up getting a pretty nice equation in terms of v and u then. One thing you have to make note of is you have to make note that v itself should be equal to x over t, or accordingly, delta x over delta t rather, where all of these deltas are just saying relative to zero. Because remember, everything here started at the point 0, 0, or 0 for everything rather. So quite nicely. So I could say, for example, that, okay, well, delta x prime should equal gamma delta x minus u delta t. I could say that delta t prime should equal gamma delta t minus u over c squared delta x. Remember that u is actually a constant velocity, so all that's changing are the x's and the t's here. Now, if I take delta x prime over delta t prime, the gammas cancel, and I need to erase something. I'm going to go ahead and erase my picture now, actually, just to free up a little bit more room. That actually then tells us that delta x prime over delta t prime equals delta x minus u delta t over delta t minus u over c squared delta x. Now, what I'm going to do is I'm actually going to divide the entire denominator, or rather factor out a delta t. So if I do that, I get 1 over delta t. On the numerator, that still stays the same for now. And then in the denominator, I have 1 minus uv over c squared, noting that v itself is equal to delta x over delta t, which happens when I factor out a delta t. So that's pretty nice. Now, if I move that 1 over delta t and multiply it to the top, I end up with something that's actually quite nice. I get v minus u over 1 minus uv over c squared. And so now that actually tells me, okay, well, since v prime is delta x prime over delta t prime, then in frame s prime, the velocity of some third object or some third event that's happening is equal to the velocity that somebody in frame s witnessed minus the velocity of frame s prime itself over 1 minus uv over c squared. This is actually kind of a nice little result then. And if we go over to our next little bit, then you can actually see that equation typed out as well. So that's actually kind of a nice, lovely equation. You can also do the opposite. You could actually also take inverse, and if you know all of the primed coordinates, then you could find the unprimed coordinates via similar equations as well. Those are called the inverse Lorentz transformations. They're derivable in much the same way that the actual Lorentz transformations that we just covered, those three equations that I showed you, they're derived in much the same way that those ones were, right? If you're curious, you could either try to do some sort of geometry argument like we did in the previous slide, or you could actually just rearrange the equations that we had and solve, and you would get these three inverse transforms. It's honestly probably easier, I would say. So feel free to try that out if you wish. The good news is that typically in practice, especially with elementary relativity problems, you don't have to rearrange the equations because whatever you're looking for could just be solved based on the appropriate equation. We have six of them now, right? We have an equation that solves for x prime, an equation that solves for t prime, an equation that solves for v prime, and then likewise for the unprimed equivalents. Now, of course, all of that depends on what you're actually provided in the problem. So, like, if you for some reason knew one of the primed coordinates and you wanted to find another primed coordinate, then perhaps, yes, you would need to rearrange these equations. But typically, that's not really the case. Typically, you know information from one frame of reference, and you want to find information in another frame. So let's take a look at an example. So in this example, I travel in a spaceship that is at a speed of 0.5 c relative to you, and your clock measures the journey to take 1 times 10 to the 6 seconds. That's also 0.03 years. I've done that conversion for us. How far did I travel in your frame? And how far did I travel in my frame? And in addition, how long did the journey last on my clock? So this is kind of like a classic length contraction time dilation problem that we have. So if we want to figure out how far I traveled in your frame, all we have to do is just take the speed and multiply it by the time. So that tells me that, okay, well, you were the person who was at rest. You're going to have the unprimed coordinates. My velocity relative to you is given by the letter u. That's 0.5 c or 1.5 times 10 to the eighth. If I multiply that by time, which is also given in your frame of reference, the unprimed t value, then that gives me the distance that I traveled in your frame. Now, if I want to find the distance that I traveled in my frame, right, or what my actual kind of like odometer would read if my spaceship has one, I'm looking for x prime. And the Lorentz transformations tell me that x prime should equal gamma x minus ut, and we actually have all of that stuff. And sorry, I misspoke. It shouldn't actually be what the odometer is reading. It's how far I perceived or how far I register myself as moving. You'll probably notice something that if I'm trying to perceive how far I have moved, well, look at what x is equal to. X is equal to ut. So if I take x minus ut, then I end up getting an x prime value of 0 because I'm always stationary relative to myself. So that works out exactly how we expected. And then if I want to figure out how long the journey took for me, I would still obviously perceive some measure of time. How I can actually do that is I would be looking for t prime. So in order to find t prime, we would go back a couple of slides to that second equation right over here. And so if I plug in the numbers there, I end up getting 0.027 years, so slightly smaller than 0.03 years. If you convert that to seconds, it's actually a fairly noticeable difference in terms of number. It's 866,000 seconds compared to a million seconds, which is, in terms of numbers at least, a fairly big difference. In terms of seconds or in terms of years, maybe not. It's probably a couple of days at least. So, yeah, but that kind of makes sense then. My clock would run slower since I'm moving relative to you, and therefore I would record a smaller time. So that's kind of just a very simple way to actually use the Lorentz transformations. Again, you could actually also use them if you have a third object moving relative to both of us too. So that would actually be allowing us to use the full power of the Lorentz transformations, including these v and the v prime equations as well too. If I wanted to figure out the velocity of, say, a spaceship moving relative to both of us, I would have to know its velocity relative to one of us, and then we could apply the appropriate rule to do so. So it's actually kind of cool how all of this stuff goes together then. Length contraction, time dilation all get wrapped up nicely in this very lovely set of six equations that we can use to solve for different distances and different times. So that's it for this section, actually. In the next section, we're going to talk a little bit more about how energy and momentum transform in relativity. And that's actually obviously very important for a lot of different topics, especially when you're thinking about particle physics too. So that'll be a fun little video for us to talk about. All right, but in the meantime, thanks so much for watching, and I'll see you guys in the next video.